Okay, we're midway through the course, so let's take one lesson here and review everything we've done so far, the highlights and the things you want to make sure you have solid going forward. So I guess we began by mentioning that calculus and most all of mathematics is based on the idea of functions. And a function you can think of as just a machine where you stick a number in and the machine does something to it and spits a number out. And for any number that comes in, only one number that comes out. And so then we can make ourselves a called a Cartesian plane, where we plot points, and the point that we plot has the property that the x value, that is the distance along the horizontal axis, which is the x-coordinate, that's the number that you put in, and then the y-coordinate, the number that comes out, is the value of the function. And by doing that, you get all sorts of functions that you can graph. The graph is just a picture of the function. So then we looked at particular functions. Some were lines, and we mentioned that lines are important because a lot of things in the natural world have this linear property. The most important thing about a line is the slope of the line, which basically tells you that if you move a certain distance in the horizontal direction, how much do you move in the vertical direction? And the slope is defined to be the change of y over the change of x. This is the change of y, this is the change in x. And given a point on the line, AB, and the slope m, then we can find the equation of the line just by saying, well, if xy is just some general point on the line, what property does xy have to hold? And the answer is the change of y over change of x has to be m, so y minus b divided by x minus a has got to be the slope, which means that y minus b is the slope times x minus a. And that's, I think, by far the most useful and convenient equation for a line. Then we also talked about exponential functions. Exponential, recall, are ones that have, especially e to the x, where e is this particular number between 2 and 3, has the property that whatever the height of the function is, the slope at that point is the very same value. So as the height increases, the slope increases exactly the same. If you have something like 2 to the x, it has a similar property where the slope is proportional to the height, but almost basically the same thing. So that was e to the x. Then the inverse of e to the x, which you get by flipping it over the line y equal x, is called the ln of x. I guess this should be y equals that. And that had a lot of interesting properties too. I guess the two most important for the ln of x is that the ln of a times b is equal to the ln of a plus the ln of b, and the ln of a to the b power is equal to b times the ln of a. Okay, the exponential, in contrast, had the property that e to the x, I'll write it a plus b again, e to the a plus b is equal to e to the a times e to the b, and e to the a all to the b power is equal to e to the ab. Feels like alphabet soup. Okay, so that was the exponential. Then we had the trig functions. Excuse me. And remember, the trig functions we got by looking at a unit circle and asking what are the coordinates. If this is the angle theta, what are the coordinates of this point? If this radius is 1 and the x-coordinate is defined to be the cosine of theta, the y-coordinate is defined to be the sine of theta, And so another way of thinking about sine and cosine is that if you have a triangle, it amounts to the same thing. This is theta. This is the way you sometimes see it as well. This is opposite. This is adjacent. And there's your hypotenuse, that the sine of theta is the opposite over the hypotenuse, and the cosine of theta is the adjacent over the hypotenuse, and the tangent of theta is the opposite over the adjacent. Okay, so those all amount to the same thing as this if you just put in the values. So that's trig. Once you have that, then if you want to graph the sine, for example, the sine graph looks something like this. There's pi, there's 2 pi, this is theta right here, and this is sine of theta, and pi over 2. This goes up to 1, down to -1. The cosine of theta looks similar. It's going to start here, go down there, here, back up there, back up like this, and so on. So it's just translated over. So that's those are the functions we looked at. Then we got into this new idea, and we said, given functions, given a particular function, if you think of the graph of it, we're not only interested often in the height of the function at a particular point, we also want to know how fast is the function changing right there, or in other words, what's the slope of the function at that point, by which we mean what's the slope of the tangent line to the function at that point. And so we got hold of that problem by saying, well, let's move a little bit away to say x plus h, and let's find the value of the function there as well. So that's going to be x plus h, f of x plus h. This right here is the point x, f of x. And then we will find the slope of the secant line, the line that goes right between those two values. And so, as always, it's the change in the slope is the change in the y values minus, or I should say divided by, the difference in the x values. X plus h minus x is just h. And that right there gives us the slope of this secant line, which goes between those two values. But that's not good enough. We want the slope right there. So then what we do is this just incredible, cool idea, which someone came up with, it's a combination of people, said, okay, let's take the limit of this quantity as, in order to get this thing pushed into it, we need to take h and let h go to 0. And this we defined to be the derivative of the function at the point x. And so that gives us the slope of the tangent line. And notice, you might say, well, if the secant lines are all gotten by taking this difference and so on, why not just let h be 0? If h is 0, won't that be the slope of the tangent line? Well, if you just let h be 0, you're going to get f of x minus f of x, which is 0 on top, and you're going to get 0 on the bottom. 0 over 0 is undefined. So just letting h be 0, which seems like the natural thing to do, it just doesn't work. So we do the next best thing. We take the limit as you approach 0. And so it's the way to get around that problem. It's just very clever. And so that does it, and that gives us the slope. So once we had that, we applied it to different functions. And so, for example, we applied it to, let's apply it to square root of x. So here's square root of x right here. And so here's x plus h. And so you do the same thing here. And so now this is just going to become the square root, and this is going to become the square root. And then you need to actually evaluate it. Okay, you need to actually figure some way out to evaluate that thing. And remember, if you might remember, the way we did this one was we multiplied both the top and the bottom by the conjugate. X plus h plus square root of x. Same thing on the bottom. As long as you multiply the top and the bottom by the same thing, you are good. You haven't changed anything. And if you do that, then as h goes to 0, the top becomes, multiply it out, you're going to get x plus h. The inner and the outer, they cancel each other out because this and this are the same. One is negative, one is positive. And then you subtract x by multiplying these together. And on the bottom, you get h times the quantity. Like so. And now your x's cancel out. And once your x's cancel out, now we can divide out this h with this h. Left with a 1 on top, and as h goes to 0, you get square root of x here, square root of x here, which is 1 over 2 times the square root of x. So we did that for lots of different functions, and we discovered in particular that they all kind of obeyed the same property, and that is that if you want the derivative of something of the form x to the r power, that just ends up being r times x to the r minus 1. And then we found lots of other derivatives as well. Very good. Then we also did the product rule and the quotient rule and things like that. And then we started applying our calculus to solving some problems. And so this is let's do a couple more problems like it just to reinforce the idea. So suppose you've got a function similar to the one I just drew. Suppose it is y is equal to the cube root of x. The cube root of x. And suppose we want to find the cube root of 128. Okay, 128. And so what we do is we first find a number close to 128 for which we can easily find the cube root. It's an exact value. And notice that the cube root of 125 is 5, right? 5 times 5 times 5 is 125. So there's a value on the graph. So then remember what we did? We said, okay, let's find this line right here. We need the slope of it. We already have a point on it. And then we'll use that line to approximate the value of the function here. And I really exaggerated this thing just so I could show you the difference. But in actuality, this is going to be very close to that. So let's do it. So first of all, here's our function. F of x is equal to, I'm going to write it as x to the 1/3 power. So f prime of x, the derivative, is going to be 1/3 times x to the negative 2/3 power, which is 1 over 3 times the cube root of x squared. Okay? Make sure that that's clear. Okay? So we want to evaluate that at 125. That's where we want the slope. So the derivative at 125 is 1 over 3 times. Now, I can either take my 125 and square it and then take the cube root of that, or it's just as convenient, or actually it's more convenient, but just as correct to do this thing first. To first take the cube root of x and then square that. Either way, you end up with x to the 2/3 power on the bottom. So notice it's more convenient to take my 125 and take the cube root, that's 5. 5 squared is 25. So that's going to be 1 over 3 times 25, which is, of course, 1 over 75. So that takes care of that. So now what's the equation of our line? Our line is going to have equation y minus 5 is equal to, here's the slope, 1 over 75 times x minus 125. And then you can add 5 to the other side. Get rid of this now. And finally, in order to approximate the value here, you just stick 128 into this function. So if you stick in, I'll say 128 here, what do you get? 128 minus 125 is 3. 3 over 75 is going to be 1 over 25 plus 5. So that would be 5.04. And you check that out, and hopefully you will find that it's a little bit bigger than the actual cube root of 128, but you'll find that they're very, very close. So that works out pretty cool. Okay, let's do one more problem now. And this is, again, one of my favorite problems. It's a related rate problem. I did several of them already, but here's another one. Suppose you have an ant which is exploring the area, and it hops on a semicircular hoop. Okay, so here's a hoop that has a radius of 10, and this ant hops on 6 legs, couple antennae, and it's moving along this hoop at a rate of 4/3 pi inches per second. Okay, it's moving along that hoop at that fast, along the top of it, and we want to know how fast is it gaining or losing height at t equal 5 seconds. At 5 seconds. So if it's still going up this side, it'll be gaining height. If it happens to be over here, it's going to be losing height. Okay? So how fast is it gaining or losing height? So recall the steps. First step is, what do we want? What we want is the height, the rate at which the height is changing. So dh dt. Number 2, what do we know? We know the rate at which it's moving along the hoop. Recall that when we talked about the definition of angles, and we said if this angle is theta, and this radius is r, and this distance is s, then what's the relationship? S is equal to r times theta. So we used s for that. So let's say that we know that ds dt, where s is this distance right here, is equal to 4/3 pi inches per second. So there's what we know. So here, as I said, is the toughest part. It's finding a relationship between h and s. And this is another reason I like this particular problem, because it's not quite so obvious how to get the relationship. Okay, it's not staring you in the face the way it is in some of the others. So you look at this for a little bit, and feel free to turn off the video and try to ponder it on your own, or pause it. But here's what I did. I said, well, let's throw in another variable here as well, theta. And so here's what I know. I know that s is equal to r theta, and I also know that that h over 10 is equal to the what? Is the sine of theta. So in other words, h is equal to 10 times the sine of theta, and then theta is going to be equal to s over r. And r is just equal to 10, so s over 10. So there's a relationship right there, which you had to get by looking at these other two and putting them together. So here you have it. H of t is equal to 10 times the sine of s over 10. Okay, very good. So now that's the hard part. Now we can go ahead and take the derivative. And so we're going to get dh dt is equal to 10. The derivative of the sine of anything is the cosine of that thing. Times the derivative of the thing inside. So we have 1/10, or we have s over 10, so the derivative is going to be 1/10 times ds dt. Just like if you had x cubed, 10x cubed, the derivative is going to be 10 times 3x squared. So it's 10 times the derivative. So we have that. Now we can evaluate it. Let's see. So we want let's go up here. So we want dh dt when t is equal to 5. So we're going to get 10 times the cosine of, well, let's see, s. This poor ant is moving at 4/3 pi inches per second. So after 5 seconds, 5 times 4 is going to be 20 pi over 3. So s is going to be 20 pi over 3. Let's do a couple steps in one. This s is 20 pi over 3. If you divide it by 10, it's going to be 2 pi over 3. So we're going to get cosine of 2 pi over 3 times 1/10 times our ds dt, which is 4 pi over 3. Okay? Well, what is the cosine of 2 pi over 3? I always like to draw the unit circle again. Pi over 3 is right there, that's 60 degrees. 2 pi over 3 is right there, that's 120 degrees. The cosine is this part right there, which is -1/2. So it's going to be 10 times -1/2 times 1/10 times 4 pi over 3. Notice the 10's go away. The 1/2 cancels with the 4. You still have a negative right there. So it's going to be, you end up with a 2 there. So it's going to be -2 pi over 3. And the units would be inches per second. So the ant's on its way down. So when I first taught my class back in 1982, I think it was, I put that on there. I had 2 classes of calculus, and no one got it correct. And so I told them I'd give them a similar problem the next week. And before I gave them the similar problem, I gave them a bogus problem where I had this thing and then I had a whole bunch of different little semicircles connected to that and other ones on that. And I just wanted to see what would happen when they all got this sheet of paper with this quiz. And most of them just all started writing away, and I thought, what the heck are they writing? There's no way they can do it. The sharpest kid in the class, he was in the very back of the room. When he got it, he just looked up at me and smiled. He just thought it was a joke right away. But anyway, it's a good substantive problem. If you know this one, you probably know you can do just about anything anyone throws at you. So there's the first half of the course. We'll start talking about graphing functions next time. See you.